Inverse trig worksheet 2. This is focused more on the graphs for inverse trig, and I don't have a lot of graphing questions on the tests that we're going to have, but we will have problems like this on our AP exam, so I wanted to practice this a little bit while we're in this chapter. Okay, so identify each graph. I would like you to know out of these three parent functions, which one is arcsine, which one's arccosine, and which one's arctangent. And the easiest way to figure this out, I think, well, first of all, arctangent is the only one that looks pretty different. It goes on forever in both directions. So this is definitely the graph of arctangent. Arctangent can either be written this way or inverse tangent x. It doesn't matter. What about the other two, though? How do you know which one's sine and which one's cosine? Remember, I do need you to evaluate these inverse trig functions. So remember, the range of arcsine is the positive pi over 2 to negative pi over 2. Those are the answers we're allowed to get when we're evaluating arcsine. So look for the graph that does that. This graph goes from negative pi over 2 to positive, whereas this graph goes from 0 to pi. And that's the rule for evaluating arccosine. Okay, so the first one is the graph of y equals arcsine of x, or inverse sine. You've got to know that those are the same thing. What's the domain and range? So you can use the graph here to remind yourself the domain of this graph is negative 1 to 1, and the range is negative pi over 2 to pi over 2. So when we evaluate, remember, arcsine problems, we only get answers between negative pi over 2 and pi over 2. And the only numbers, if you go back and look, the only numbers I'm putting into inverse sine functions for you to evaluate are values between negative 1 and 1. So this next graph, because it goes from 0 to pi, I know, and it's this shape, I know that it's y equals arc cosine x. I know these two shapes are similar, but arcsine is an increasing graph, arccosine is a decreasing graph. The domain of arccosine is also negative 1 to 1, but its range is 0 to pi. And then finally, for our arctangent graph, there are arrows here. There are horizontal asymptotes at pi over 2 and negative pi over 2. And that means that pi over 2 is the value that we approach on the right, and negative pi over 2 is the value on the left. So the domain here is all reals, and then the range is between negative pi over 2 and positive pi over 2, but not including the endpoints like we do for arcsine. Okay, so it's good to have these graphs in your mind because, again, when we do our AP Classroom problems, we'll be looking at transformations of these graphs, especially shifts and dilations. So just to practice what that looks like in inverse trig before we actually graph anything, or before we look at graphs. For each function, use the function notation to describe the transformation. So I've got to describe what's happening here, just in general, and then write that equation with the transformations included. So when there's a 2 out in front of a function, that is a vertical dilation by a factor of 2, and that's because every y value gets multiplied by 2, so that's the factor. We also have a horizontal shift. You could just say shift to the right 4. You do need to indicate the direction, and a vertical shift, or just a shift, because we're going to say up 1. And then what would that look like in this equation? So that would be like, I'm just going to call it y equals, since I used f of x there. There'd be a 2 in front of the arcsine. Inside of arcsine would be x minus 4, and outside of arcsine would be plus 1. Okay, so if we have this, actually, I think I put this inside of the function. I think I changed this on yours to be f of 1/2 x, or x over 2 or something, minus 3. So if that's the case, it's a horizontal dilation by a factor. It's not a factor of 1/2, it's a factor of 2, because remember what's happening to every x value? Every x value gets divided by 1/2, which is really multiplied by 2. So the factor is always what are you multiplying x or y by. We also have a vertical shift down 3 units. And if I put those transformations into this function, it would be something like y equals inverse cosine of x over 2, and then the minus 3 would be on the outside. Okay, so kind of keeping that in mind, on the next page, I've given you a graph. It's got some sort of transformation. So you have to know which shape it is, and then also what has happened to it. So first graph is that sideways opening graph with no endpoints, so that's got to be arctan. So we know it's an arctan shape. And what's happened to it, it's kind of hard to tell the dilations on here if there are any, but oh, and I just realized I don't have any horizontal axis showing. This is still pi over 4. Sorry about that. And this is pi over, oh, I'm sorry. No, it's not. This value here is still 1, and this is -1. Sorry about that. Okay, so I know this hasn't been dilated because we're still a fourth of a unit above when we hit 1 and a fourth of a unit below when we hit -1. But this graph has been shifted up. Normally it goes through 0, 0. So it's been shifted up pi units. So I just need to write an arctangent equation in either form, doesn't matter, where the only thing that's happened is a vertical shift up pi units. The next graph is an increasing graph, so that's arcsine. So it's got the arcsine shape. Okay, and it has not been shifted vertically because it's still going through 0, 0. But normally arcsine starts and stops at this -pi over 2 and pi over 2 after 1 unit, and here it's being stretched out to 2. So it's gone through this horizontal dilation by a factor of 2, and that means that every x value got divided by 1/2. So that means that when we write our equation, it should be y equals arcsine or inverse sine of x divided by 1/2. So when I see this, that tells me that there was a 1/2 in front of the x, and there's no vertical shift, right? Because if we see this, we say, oh, take every x value divided by 1/2. Okay, and our final graph, oh, not our final, our almost final graph. This one looks like a decreasing function, so it's got the arc cosine shape. And normally arc cosine hits 0. At 1, it hits 0. And at pi, at -1, it hits pi. So it normally looks like this. So this has been gone through a horizontal shrink, horizontal dilation, by a factor of, again, it looks like it's half its size, so a factor of 1/2. Now, what does that mean? That means that every x value got divided by 2. And what does that mean? It means that we put a 2x in the parentheses. So this is arc cosine of 2x. And then also there's been a vertical shift. This point is now up pi over 2 units, so plus pi over 2. And I'll just make it an equation by making it y equals. All right. This last graph is increasing, so it's arcsine. It's going through 0, 0, so no shift. Normally arcsine between -1 and 1, it only reaches to pi over 2 and -pi over 2. But now it's reaching up to 3 pi over 2 and -3 pi over 2. So that's a vertical dilation by a factor of 3. Take your original y value, multiply by 3 in both cases. So that would be y equals 3 times the inverse sine or arcsine of x. And that's it for that one. All right, find the inverse function for each. So we did this a little bit in our notes with logarithms and exponentials, and then here we are again with trig. So to find the inverse function, we're given a restricted domain, so we know there is an inverse function. switch your x and your y, so make this x equals 2 times the sine of y. And remember, it's a good idea to come up with domain and range because we're going to have a restricted domain for our inverse function. So this sine graph is graphed from negative pi over 2 to pi over 2. It's got an amplitude of 2, so its range will go from negative 2 to 2 instead of negative 1 to 1. That's going to become the domain for my inverse function. Okay, so back to this. Switch x and y. You want to solve for y, so isolate sine y, so divide by 2. And then how do I get rid of a sine function? I inverse sine both sides. So the inverse sine of x over 2 equals the inverse sine of the sine of y. Inverse sine and sine can cancel out, and we're just left with y equals. And then for my final equation, I need to make it f inverse equals inverse sine of x over 2. And I also need to create the domain restriction because it's not true that this is graphed forever and ever. It's only for x values between negative 2 and positive 2. So you're always just using the range, and this is just the range of a sine function with an amplitude of 2. That range gets applied to become the domain of the inverse function. Same thing for this one. Let's look at this cosine graph. It's got an amplitude of 1/2, no vertical shift. So its range, the range of f, goes from negative 1/2 to positive 1/2. And so if we switch x and y, x equals 1/2 times the cosine of pi over 2 times y. Isolate the cosine part, so multiply 2 over to this side. Get rid of the cosine by taking the inverse cosine of both sides. So inverse cosine that side, you just have pi over 2 times y. Get rid of the pi over 2 by multiplying by 2 over pi. So f inverse of x is equal to 2 over pi times the inverse cosine of 2x. What's the domain on that? It's the range of f becomes the domain of f inverse. So negative 1/2 less than or equal to x less than or equal to 1/2 should be our inverse function's domain. Okay, last example on this type. So same idea. Switch. Let's come up with range. Sorry. So remember, a tangent function has those branches that do one of these. So the range for this tangent function is all reals. So that means when we come up with inverse tangent, which we know goes on forever, it also has a domain of all reals. So switch your x and your y. Oops. Make that tangent of y minus pi plus 2. Isolate the trig function always. So subtract 2. Divide by negative 1. Now when you do that, that's going to become negative x minus 2, or you could say 2 minus x. Just distribute the negative through, switch it around. That would also be what you got if you said, I'm going to add tangent to this side and subtract x over here. So either way, inverse tangent both sides. So inverse tangent of 2 minus x, inverse tangent crosses that out. You're left with y minus pi over there. We're going to add pi to our final answer. So f inverse of x is equal to the inverse tangent of 2 minus x and then plus pi. Domain is all reals. I like to write that either way, but you wouldn't have to because that's not a restriction. Okay, final thing. Again, I modeled these to kind of help us with our AP classroom after this. So solve for theta using inverse trig. This is something we actually did way back in I don't even know, section 4.3 or something, like our first half of the chapter. So if I want to solve for theta, I would first set up the proper trig equation. So I have opposite, hypotenuse. So sine of theta is equal to 5 over 7. And again, if I want to get rid of the sine, then I inverse sine both sides. So the inverse sine of 5 over 7 is equal to theta. And on this one, because I have opposite and adjacent, I would use tangent to begin with. Tangent of theta equals 2 radical 2 over 4. And let's simplify that. 2 over 4 on the outside makes this radical 2 over 2. Solve for theta by taking the inverse tangent of radical 2 over 2. And that, by the way, is not pi over 4 because it's inverse tangent of radical 2 over 2. So for both of these, if we wanted actual numerical answers or decimal approximations, we would have to use our graphing calculators. All right, that's it for worksheet 2. After this, we're going to do AP Classroom. So this is just sort of like a kind of like a warm up to get you used to what those questions will look like.